Let's now go to sample exam 3, question number 7. This is a trend question, trends in the periodic table question. So I've placed a periodic table right here at the bottom of the question just so that we can have it as reference. This question asks about the trends in atomic and ionic radii. So we have to think about atomic radii first. And all trends are based on analyzing the energy of the electron using this equation right here, right? Z effective squared over n squared times negative of a constant called the Rydberg constant. Generally, we expect the following trends for elements in a period and a group. Okay, so across a period for atomic radii, so we go from left to right across a period, we expect the atomic radii to decrease. And the reason for this is because the Z effective component is increasing the effective nuclear charge, but the principal quantum number stays the same as you go across a period. So as a result, because there's more nuclear attraction to the valence electrons, the size gets smaller. And then when you go down a group, we expect an increase in atomic radii. And the reason this is because the Z effective is increasing, but not as much as the principal quantum number is increasing. And therefore, overall, the energy becomes weaker. That's holding the valence electron. And so the size correspondingly becomes larger. And so let's take a look at those trends in atomic radii first, and then we can take a look at the ionic radii after that. So if we look at the atomic radii, we have two choices there. One is A and the other one is C. If we look at A, we have phosphorus, I'm just going to circle them in the periodic table, aluminum, magnesium, and sodium. And so those are all in a row. So what should happen is we're going left to right. Phosphorus should be smallest, followed by aluminum, followed by magnesium, followed by sodium. And in fact, that's what we see here. So that is a correct trend. And the question is asking for the one that's not correct. So that wouldn't be your answer. And then now we're looking at option C, which is also atomic radii. And for this one, we have F, fluorine, P, aluminum, and calcium. This one is a little bit different, but as we remember, the trend is that it goes smaller as you go that way. That tells you that F would be the smallest one, followed by P, followed by aluminum, and then calcium being the largest one. And in fact, that's exactly what we have here in the choice, so that would also be correct. All right, so now we're done with the atomic radii options. Both of them are correct, so we got to look at the ionic radii. Ionic radii, there's basically two options. You have the same trend as the atomic radii, generally speaking, right? So same as atomic radii. However, if you have something called the isoelectronic series, which is just ions with the same number of electrons, then the only thing you need to do there is look at the number of protons. The one with the most protons, i.e. the one with the largest atomic number, would then be the smallest. And again, we come to this conclusion by looking at that same binding energy equation that I showed you at the beginning, that if the number of protons is large, that affects your Z effective. If the number of electrons is equal, which is true for the isoelectronic series, then the n value is the same. So if the Z increases and the n value stays the same, then the binding energy is going to be stronger, which means the size of the ions would be smaller. So let's take a look at B. So B has germanium, potassium, sulfite, and phosphite. If you look at the last three, potassium ion, sulfite, and phosphite, they actually all have the same number of electrons, right? They all have 18 electrons. Now, the germanium 4, that has 28 electrons. So you might think that I can analyze the isoelectronic series right here, and then this one would be a different one. Now, if you just look at the isoelectronic first, the 18 electrons, you see that the one with the most proton is potassium. So potassium would be the smallest then, followed afterwards by sulfite, which is then followed by phosphite. So that part seems correct. So then the question is, where do we place the germanium? Well, germanium, even though it has 28 electrons, if you write out the actual configuration of germanium 4+, it ends up being Ar and 3d10. If you end up writing the configuration for germanium 4+, it actually turns out to be similar to those other three that we just talked about. Let me start with germanium first. Germanium has 32 electrons, so its configuration would have been Ar 4s2 3d10 and then 4p2, right? Now, if I want germanium 4+, which is removing 4 electrons from the germanium atom, remember that when you remove the electrons from the atom, these guys right here is the valence electrons. They're the furthest away from the nucleus, so they're the ones that are taken out. So the configuration of germanium 4 is actually argon and 3d10. Now 3d10, that means that this is in the third shell, or n equals 3, but so is the three elements that we discussed earlier, which has 18 electrons. Those have configuration of argon, which is 3s2 and 3p6, right, with neon to start with. In other words, all these four elements, they really have valence electron in the third shell, which means their n is equal to 3. So if their n is equal to 3, that means that n is the same, but then Z effective changes, so the Z effective will be the one determining the size of the ions. In this case, germanium-4 has 32 protons, and then the largest number of proton before that would be potassium, which is 19 protons. So as a result, germanium would then be the smallest of all these four ions, and so the option that's given there in B is actually correct. Okay? Now that we finished with that one, we're going to look at our last option, which is all the halide ions, fluoride, chloride, bromide, and iodide. And this is one where they're all in the same group, so their trend is going to be very similar to the atomic radii. That means that if you're in a group, it should increase going down. So fluoride would be the smallest, iodide would be the largest, and that's exactly what we see here as well. So that tells us that all of the configuration that's given is correct, so the answer is E.